what we're going to do now is we're going to try to come up with a way of calculating the center of gravity, or in this case, the centroid. We're not going to deal with center of mass yet. The centroid of composite areas. So let me propose to you a problem. This is actually example 9.10 from your book in case you want to look at it later. And in this problem, we actually have a composite shape, a shape that has, or that is formed by different shapes. So we have this element here. And we can give some dimensions, right? We can say that this triangular portion is 3 feet in length, that this rectangular portion is 2 feet in length. This rectangular portion is 1 foot in length, 1 foot in height, so it's actually a square portion. And then we have 2 feet in height here. So this is our shape. And I would like to know the centroid of the shape, the coordinates to the centroid of the shape. If we want to give coordinates, we need to set a coordinate system. So I'm just going to set my x-axis to be horizontal. I'm going to set my origin here, and I'm going to set my y-axis to be vertical. Now, where is the centroid of this shape? Can anybody tell just by looking at the figure? Or do you think we need to do some math, maybe? Math first? Okay. And that's true. I mean, you can't really tell intuitively. I mean, you can kind of tell somehow, maybe guess, estimate. For example, remember that if your shape is homogeneous, then center of mass, centroid, center of mass are in the same place. And if that's the case, you should be able to balance them on the centroid. So you can try to kind of like picture this shape and try to picture yourself balancing it. Like, where would you be able to balance it? So from my perspective, and this is not really to scale, this is 2 feet, this is 1 foot, this is 3 feet, but from my perspective, it seems like there's more weight on this side than there would be on this side. So I feel like the centroid should be somewhere here, but notice that there's not a lot of weight here, not a lot of weight there. So maybe the centroid should be somewhere down here. We don't know yet. But what we do know is that if we were to calculate the centroid of these individual shapes, this square, this rectangle, this triangle, I think we do know those centroids, right? Pretty easily. The centroid of a rectangle is in its center. Centroid of a triangle is at 1/3 from its wall, or 2/3 from its edge or corner. And we're going to try to use that theory, what we already know, in order to find the centroid of a composite shape. So whenever your element can be divided into multiple simpler shapes, we're going to call it a composite shape. Now, in order to figure that out, let's first review our definition of a centroid. We know that the centroid in the x-coordinates is the integral of x squiggly. This is a two-dimensional shape, so I'll just use an area, but you know that it can be volume or length depending on what you are actually studying, right? So we have the centroid of this element here. But I'd like to ask you, just from a physical perspective, what do these terms mean? So we're looking at the integral of x squiggly dA. So what does x squiggly mean? What does that represent physically? X squiggly? Okay.
It's the centroid of an infinitesimally small.
Okay, the centroid of a small element, right? A really small element. So this x squiggly, really physically what it represents is the centroid of a small element. And actually, I'm just saying one element, right? Because integral, you add them up. So you add multiple, but each x squiggly is one element. And what does this dA represent? Just dA, not integral dA, just dA. The area of that element, right? This is x squiggly dA. So whereas x squiggly is the centroid of this one element, dA is that element's area. Let me show you one element. Now when we integrate, we're essentially adding up these infinite number of elements. And then we divide it by the integral of dA. So we already defined dA as the area of one element. What happens if you integrate over dA? What does that give you? dA is the area of only one infinitesimally small element, but what about integral dA?
Give you the length of that element.
I wouldn't say integral dA gives me a length. What do you think? What else do you think it may give me? Remember the area of the whole element, right? The whole shape. So whereas dA is the area of one element, when you integrate over dA, you're adding up all the infinite number of dAs, and that just gives you the area of the body. I'm going to call it the body. And I want to make sure that we understand these terms, because I feel that if we have a good idea of what each of these terms in this equation mean, then we could use that information, right, to help us, right, to help us come up with an equation that will allow us to calculate the centroid for a composite element. You know that these integrals, typically we integrate over a curve that represents the boundary of the element, right? And normally those curves are either given or easy to find, something like circles, triangles, etc. One example, which we may have done something similar in class, but one example would be the integral of an ellipsoid, right? We did this on Monday's class. If you didn't see it, that's all right. So we did an example where we had a shape, right? Some area that was bounded by the x-axis and an ellipsoid curve. So that was the area. We wanted to find the centroid of that area. We integrated over this curve from x equals negative radius to x equals radius of the ellipsoid. So we did that integral, and we found our centroid. However, notice that, and this is something from math, if you are integrating, let's say this curve is a function of x. So y equals a function of x. This is a curve. If you want to find the area under this curve, you can integrate over the entire function of x dx. And let's call this negative r. This is 0. This is r. So you can integrate from negative r to r over this curve and get the area of the element. Is that correct? Do we agree on that?
Yeah.
Now, mathematically, notice that this is actually the same as if we were integrating over 1/2 of the curve and then adding the integral of the other half of the curve. In other words, this is actually the same as integrating from negative r to 0 of that curve and then adding to it the integral from 0 to r of that curve. Is that correct? Okay. Now, why do I want to do this? Not because I want to complicate the equation, but what we can get from this is that we don't need to have just one equation, one curve. We can have multiple equations of a curve and then just add them up. And that's the same as if we were integrating over the entire element itself. So for example, if I wanted to separate this ellipsoid into 2 halves, I could say, right, and this is just kind of in theory, I could say that the centroid of this ellipsoid, x bar, can be found by integrating x squiggly, and I'm going to call this area 1 and this area 2. So I say that the centroid can be found by integrating x squiggly 1 over this first area, then dividing it over the integral of dA1. However, because I split it up into 2 curves, I can add the integral of x squiggly for area number 2, and then integral of area number 2. So if you look at this equation for the centroid, it means the same thing as this equation. In this equation, we are integrating from here all the way to here. And here, all we're doing is integrating from here to here, and then adding the integral from here to here. Same thing with the areas. For this area, we're integrating all the curve. Here, we're integrating half of the curve, and then adding the integral of the other half. So even though the equation looks longer, bigger, you'll see that we we still have the same thing. We'll still land in the same answer. Can we agree on that? That we'll have the same answer even though we split it up into two terms? Okay. And here's why I'm getting, here's why we want to do this. Ideally, right, I could say, and just mathematically, I can say that the integral of dA, let's say dA1, over the integral of dA1 equals what?
1.
Okay. And the integral of dA2 over the integral of dA2 equals what? Okay. So what does this tell me? I can multiply any term in this equation by 1 and it doesn't change the final answer, right? So that means I can multiply any term in this equation by integral of dA1 over integral of dA1 or integral of dA2 over integral of dA2, and it won't change my answer, right? You multiply by something, then divide by the same thing, the number doesn't change. And that's what I'm going to do now. I'm going to integrate, and try not to lose so much. Let me write the equation again. X bar, I'm going to multiply the terms in this equation by dA1 over dA1 and dA2 over dA2. So let me just write these down first. This is x squiggly. So this was the equation that we had originally. We know that this is no different from this equation. We're just splitting up the terms. But now if I multiply this term by dA1 over dA1, I can say that this is all this multiplied by dA1 divided by dA1. And I'm going to multiply this term by dA2, or integral dA2. I keep saying it and forget to say integral. And divided by integral of dA2. Now, what does this represent? Integral of x squiggly dA over integral dA. What does this represent? Where have we seen that equation? Integral of x squiggly dA over integral dA. That's just a centroid, but it's only for dA1, so that's a centroid of what?
First area.
Of the first area, right? So this, as you can see here, is the centroid x bar of my first element, my first segment, which is my number 1 segment. And this integral of dA, what did that represent? Integral of dA? Yeah, area of that first segment, okay? So area 1. Likewise, we have the centroid of the second segment multiplied by the area of the second segment. And believe it or not, this actually gives us a very simple way of finding the centroid of a composite area like the area I have drawn here. Because now I can say that for a composite area, the centroid x squiggly is located or can be found by taking the centroid, I said x squiggly, I meant x bar, the centroid of the first segment times the area of the first segment plus the centroid of the second segment times the area of the second segment divided by the sum of the areas of the two segments. Now, of course, that was if we wanted to divide our element into two segments. However, notice that we can divide this into as many terms as we want. We can divide this expression into as many terms as we want. We can integrate from here to here, here to here, here to here, and have as many segments as we want. So I think a more appropriate or general way of writing this would be that the centroid can be found by taking the sum of the product of the centroids times the areas of each segment. So from I equals 1 to n over the sum of the areas of each segment. Likewise, we can find the y coordinate of the centroid in the same way. And of course, we can find the z-coordinate in the same way. So this is how we find the centroid of a composite area. Of course, we're going to have to do some examples to make sure that we know what we're talking about. But up to this point, are there any questions with the material? So does everybody understand how we arrive at this equation? Okay. This type of sum where you want to find one value and you find it by taking the sum of the product of the value times the percentage, and this can be seen as the percentage area of the entire thing. That's what we call the weighted average. And this doesn't just apply to centroids, it applies to almost any physical average you want to find. A weighted average considers not just the value you have, but also the weight that that value has over the entire sample set. Weighted averages, for example, can be found anywhere, right? Not just in statics. Normally, on averages that you're already used to, they don't really have to be weighted because your values all have kind of like an equal weight. Like grades. If I want to find the average of a grade, I don't really have to make it weighted because I say that each of your grades has equal value, right? Equal weight, and then I just add them up, divide them by the number. However, sometimes the weight that your value has over an entire system can come into play. I was hoping I could come up with an example as I finished that last sentence, but it didn't. But yeah, nothing comes to mind. But you can figure it out yourselves. You'll see how weighted average actually become important. And I want you to understand this idea of weighted averages, because one of my issues with the more advanced classes is that when a professor or when I mention something like weighted average, normally my students just take a normal average, add everything, divide by n. Whereas we need to remember that it's not just adding everything, but also considering the weight that your value has. GPA, that's one example. Now we're talking about grades. GPA. You get a grade, right? A, B, C. I hope you don't get D's and F's, but you get A, B, or C. Which grade do you think will affect your GPA the most? A C in statics or a C in the 1 credit hour lab course?
Statics.
Why?
Because it's 4 credits.
3. It has more credits, right? So if you were to calculate your GPA, which is a function of all the credits you've taken so far, statics actually comprises 3 of all those credits. But a 1 credit hour lab would comprise 1 of those. So statics has more weight. So when you calculate your GPA, you can't just say, oh, this is the grade I got in each class divided by the number of classes. You can't do that, right? You have to calculate by multiplying the grade you got in each class times the credits for that class, and then dividing by a total number of credits. That's an example of weighted average. There we go. Can't believe it took me so long to think of that. We're in school. I should have thought about grades and GPAs. Let's go ahead and solve this example then. Ugh, this paper doesn't look nice. Let's go ahead and solve this example on a nicer sheet of paper. And again, this was number 9.10, example 9.10. And just to recap, this was our shape. We had a triangular-like shape, rectangular-like shape, and a square shape. We said that this was my y-axis, this was my x-axis. We had 3 feet. We had 2 feet. And we had 1 foot. Okay. And we wanted to find the centroid of this element. Now here's how you can find the center of this element. There's actually different ways to solve it. We have enough time, so I'm going to try to show you different ways, 2 different ways of solving it. I think the first thing we can try to do is to solve this problem by adding. Okay? In order to find the centroid of a composite element, I think the first thing you want to do is to divide your element into segments. Now this may be obvious for this one problem, but as you start working on more complex problems, then the way you divide your elements start to become less and less intuitive. So you may need to get a bit of practice here, but ideally, you want your segment to be simple enough that you can calculate your centroid easily, okay? In this case, how many segments do you think we can use? Sorry? Three? Okay. What are those segments? Good. We have the small rectangle, the bigger rectangle, and the triangle. So we can divide it into 3 segments. Does everybody agree with that, or does anybody have a different opinion? Agree? Okay, so we divide into segments. We divide our body into segments. In this case, we have 3 segments. So what does this tell me? In this case, what this is telling me is that I'm going to have my first segment, and whatever I get from there, I'm going to have to add it to my second segment and my third segment in order to get that weighted average. Okay, this is just a diagram as a guide. You don't have to draw it if you don't want to. For me, it's a good observation. So after you divide into your segments, you want to find the coordinates of the centroid for each segment. Now, in this case, it's easy. Sometimes we'll be dealing with more complicated shapes. And in that case, we may need to go over the 4 steps of setting your differential element, finding x squiggly, y squiggly, expressing your dA in terms of the differential length, and then integrating. However, in this case, I don't think we need to go that far. So let's go ahead and find, for each element, the x and the y coordinates of the centroid. So I'm going to write down, for element number 1, what is the x coordinate for the centroid of element number 1?
4, 5, 4, 5.
Remember, we're looking at it from this origin.
2.5. Negative 2.
There we go, negative 2.5 for the x. And Thomas, what were you saying for the y?
0.5.
0.5, that's correct. Does everybody agree with Thomas? I think so. Good. For my second element, what is the x coordinate to the centroid of this element? It's a rectangle, remember?
Negative 1.
Negative 1. What about the y coordinate? 1.5, there we go. Remember, that's 3 feet vertically. And finally, for my third element, what's the x coordinate of the centroid?
1.
What's the y coordinate of the centroid?
1.
Does everybody agree with Andy?
Mm-hmm.
Okay.
Can you re-explain the centroid for the rectangle for number 2?
Yeah. It's a rectangle. The centroid should be at its center, right? So because the rectangle is 2 feet in length, the x coordinate will be just 1 foot. It's half of it. Okay. And same thing with the y direction. The rectangle is 3 feet in height, so it'll be half of that, 1.5. Okay. So after we found our x and y centroids for each segment, we want to find the area of each segment. Okay, so we'll find the area for each segment. For segment number 1, what's the area of this rectangle?
1.
For segment number 2?
6.
in segment number 3? Good. So we found the centroid as well as the area of each of our elements. And now all we have left to do is to solve. Exclamation mark. How do we solve this? Well, we already know that the centroid is going to be equal to the sum of the product of the centroid of each individual element and their area divided by the sum of the area. So in this case, we have 3 segments. So my centroid x bar coordinate will be x bar 1 area 1 plus x bar 2 area 2 plus x bar 3 area 3, and all of that divided by area 1 plus area 2 plus area 3. So let's go ahead and solve this. We get the x bar equals, let's see, x bar 1, that's negative 2.5 times 1, that's negative 2.5. X bar 2, that's negative 1 times 6, that's negative 6. X bar 3, that's 1 times 4.5, that's 4.5. In the denominator, I have area 1 plus area 2 plus area 3. 1 plus 6 is 7 plus 4.5 is 11.5. Let's see, minus 2.5 plus 4.5 is 2, minus 6 is negative 4, so negative 4 over 11.5. Can somebody give me that value?
Negative 0.348.
Negative 0.348. Can somebody confirm?
Yes.
In this case, we were given units of feet, so I'll just say feet, right? We're dealing with feet, as you can see here. Good. Same thing applies for my y coordinate, right? In the y direction, I know that my y coordinate will be equal to y bar 1 area 1 plus y bar 2 area 2 plus y bar 3 area 3. Now you don't have to write down this the whole time. I just want to make sure it's all written in this class just for clarity, so you know each and every value that I am solving for. So in this case, I have y bar 1 area 1. So y bar 1 is 0.5 times 1, that's 0.5. Y bar 2 is 1.5 times 6, that's 9. Y bar 3 is 1 times 4.5, that's 4.5. And all this divided by my area, which we already calculated as 11.5. This is 5 plus 9 is 14, so 14 over 11.5. Can anybody give me that number?
20.22.
Thank you. Good. And so we have found the centroid of this element. Negative 0.348 and 1.22. Not bad. I think it looks simple enough, but are there any questions? Is everybody clear on how to find centroid so far?
Yeah.
Okay. There's another way of solving this, and whichever way you choose, of course, it's up to you. Sometimes it's easier to just find segments to add. Sometimes it may not be as intuitive, and it'll be easier to find segments to subtract. So let's solve this a different way, and let's try to solve this now. Instead of adding, let's solve this by subtraction, okay? Now in this case, I'm going to divide my element differently. I know that I have a triangular portion. I know that I have a rectangular portion. And I know that I have a smaller rectangular portion. Now what I'm going to do is, I'm going to divide my element. Let's say that I don't want to divide it this way. I can actually divide my element into a triangle, a big rectangle that actually covers all the way to here. And then an element that corresponds of this additional part, extra part that I added. So my three elements will be a triangle, a big rectangle that covers everything, and then a smaller rectangle that consists of the part that is not in my body. And from a math perspective, what would that look like? Well, let me just first give them names. This will be my area number 1. The big rectangle will be my area number 2. And the triangle will be my area number 3. Remember, area number 2 is not just this portion, it's the entire thing, the entire rectangle. So now what that looks like, I know I have my area number 1. I know I have my area number 2, which is a big rectangle this time. And I know I have my area number 3, which is a triangle. In this case, we found the centroids for each of them and we added them up. However, here, we're going to be dealing with a section that is not part of our body. So if this section is actually not part of our body, what do you think we have to do mathematically? Subtract it, right? So in this method, we're actually going to add more area than the shape actually has, and then subtract any extra area that doesn't belong to my body, doesn't belong to my shape, okay? And for this particular problem, it seems like it's doing extra work, and that may be the case for this problem, but you'll see, again, there are going to be problems where adding up areas just doesn't make our jobs easier. It's actually easier to just subtract areas. And I can show you an example in just a second, but let's try for this problem first. We already know what the answers are, so we know what to expect. So let's see what that looks like. Our first step is to divide into segments, which we already did, 1, 2, and 3. Then we want to find the centroid for each segment. So I'm going to say x bar and y bar for each of my segments. So I have my segment number 1. My segment number 2 is the entire rectangle. And then my segment number 3 is the triangle. So where is the centroid of this red portion? Negative 2.5, that's correct. Where's the y coordinate of the centroid of this portion? 1.5, that's correct.
Or 2.5, right?
Neither.
Or
2, right? Remember, this is 1, but then we have 2, and the center will be a half of 2, which is 1. So 1 plus 1 is 2. There we go. For my second portion, it's the big rectangle, the entire thing. Where's the centroid of this entire thing? The x-coordinate centroid. Negative 1.5, that's correct. What about the y-coordinate?
1.5.
1.5, that's correct. And for the triangle, we don't do anything differently, right? So just 1 and 1. Because my y-coordinate of the centroid, first off, my centroid is at the center of this rectangle, right? So I go 1 and then half of 2, which is 1. So that's 2 total.
Okay.
Okay?
Yeah.
No problem. Third step, we find the area of each segment. What's the area of this first segment? 2? Okay. Now here I want to be careful, because this segment, you can see here, we have it in red. This segment is a segment that is not part of our shape. So whenever I write down my area, you don't have to do this, but when I write down my area, I would write it as negative 2, because the area of the whole thing, right, would be the area of these two segments minus the area of that rect segment that's not part of our body. So negative 2. What's the area of the big rectangle? 9. What's the area of the triangle? Wait, we already got it, 4.5. Good. And the last step, as you know, is to solve, exclamation mark. So we can solve it relatively easily. We know that x bar is equal to x bar 1 area 1 plus x bar 2 area 2 plus x bar 3 area 3. The equation actually doesn't change. So let's just write it down. X bar 1 in this case is negative 2.5. So negative 2.5. And what is area 1? -2, right? Let's make that clear. -2, not 2. Okay? That negative is what's going to give us the correct answer. So we cannot forget it. Okay? And then x bar 2 area 2. So that's -1.5 times 9. And x bar 3 area 3. That's 1 times 4.5. And all that divided by the sum of the areas. So area 1 plus area 2 plus area 3. What is area 1? So what is area 1 then? -2, right? And then area 2 we know is 9, and area 3 is 4.5. We know, or we know what answer to expect, but let's plug it into our calculators, make sure that we actually did everything right, okay? So -2.5 times 2, okay? Times -2. Ooh, that's a big thing. So that's a +5. Minus 1.5 times 9. That should be, I think, 13.5. Plus 4.5. And all that divided by 9 plus 4.5 minus 2. What does that give, Andy?
-0.248.
Okay, good. Is that what you all got? Okay, good. So -0.348 feet. Which, of course, is the answer that we're expecting. We can repeat the same process in the y direction. So our coordinate of the centroid would be y1 area 1. So that's 2 times -2. Plus y2 area 2. That's 1.5 times 9. Plus y3 area 3. That's 1 times 4.5. All of this divided by the sum of the areas, which we know is going to add up to 11.5. Punch those numbers into your calculator, and we should get, right, 1.22 feet. Are there any questions with these types of problems? Thomas? Tyler? Ruben? Matthew? Mark? Kyle? Andy? Chris? Okay. So if there are no more questions, let's use the time we have left to solve another problem. This one's going to be a little bit more complicated, but still easy to solve. So don't worry, it's not a big deal. Okay? Let's turn our attention. By the way, I should do something with these because I just write all these and I feel like they look very nice and then I throw them away. So if anybody wants some free notes, then you can take them. So let's go with problem 9.9. Okay, it's actually one problem earlier, but I think this one's actually a little bit more complicated. So it was easier to start with 9.10. Now this problem, you may actually want to check your books because you know my skills for three-dimensional drawing are not very good. My skills for two-dimensional drawing are not very good either. So try to check your books. But in this case, let me try my best to draw my axes. I have my x-axis, my y-axis, and my z-axis. I have my orthogonal view there. And we're going to try to find the centroid of a wire. In this case, my wire essentially has a semicircular shape along the xy plane. Okay, so that means that at every point that I'm drawing here, the elevation z equals 0. Does that make sense? So the wire has a semicircular shape, which at an elevation of z equals 0, but then actually extends itself towards the y-axis, and then has a bit of a change in z elevation. Okay? Yeah, we need some dimensions, of course, for this type of problem. So let's say the radius of this semicircular shape is 60. And I'm going to refrain from using units this time. Let's just say it's 60. Say the length here of this shape is 40. And the length of this vertical drop is 20. So it's a vertical drop. Remember, it's dropping vertically in the z direction. Okay. I would like to find the centroid of this wire. Can we treat this as a composite element?
Yeah.
Okay. So if it's a composite element, let's start by dividing our elements, our body, into segments. How many segments do you think you can identify here? Remember, you want the segment to be as easiest as you can be, as simple as you can be, so you can reduce your calculations. Three? What are those three?
The half circle, the straight bar along the y-axis, and then the one in the z-axis.
Okay, so the half circle, the straight bar along the y-axis, and then the drop along the z direction. That's correct. So we divided our element into three segments. Segment number 1, segment number 2, and segment number 3. Do we have to subtract any of these segments, or are they all addition? Do we add all of them, or is there anything we have to subtract?
We don't have to add it.
Adding? Okay. Good.
We have to subtract from the y direction with the half circle.
No, remember, when I say subtract, I don't mean that if it's going to be negative or positive y. What I mean when I say subtract is, do these three segments all contribute to the entire body? Or is there anything that is not part of the body? In the previous exercise, we had a shape that wasn't part of the body, right? In this case, all three contribute. So we need to add for all three. So we divided our segments, right? That was step number 1. Next step was to find the centroid. And in this case, it'll be x bar, y bar, and z bar of each segment. So let's go ahead and do that. Let's find the centroid of each segment. I'll take 2 and 3, and one of you can start with the centroid of segment number 1.
So
Yep.
do we know that that's actually a half circle?
Yes. Yeah, that's part of the given information. Okay? I'll write it here. And remember, it's along the z-axis. It's actually resting on the z-axis. So elevation z here is 0 all the time. This is the xy plane. All right, so let's find the centroid of each segment in this problem. So I'm going to start with segment 1. Where's the x-coordinate of the centroid of this segment? It's a semicircle, right? Where the x-coordinate do you think would be? 60, right? Good. What about the y-coordinate? Wait, did you say nothing? Nice. But it needs to be somewhere, right? So where is it?
Oh, wait, the y? Oh.
Oh, z would be 0. That's correct. But what about y?
Y would be 0. Right.
You think the centroid is at y equals 0 here? I don't know. I don't feel like I can balance that here.
Yeah.
I mean, balance is not a good term here, but I don't think that if I were to draw a line, I would have the same amount of wire at each side of the line here.
I don't know the calculation to get it, but I know the number.
No? We need to get a calculator. Let's not assume that we know these things, right? Is there perhaps any method, perhaps a method that we have been practicing over the past week and a half, that will allow us to find the coordinates to the centroid of this half circle? Okay, so let's go ahead and find the coordinates of this half circle. We know that for segment number 1, what we're looking at, and if we were to look at it in the xy plane, I have my x plane, my x-axis, and I know I have my negative y-axis, right, because this is in the negative y-axis. Essentially, what I'm looking at is a semicircle, semicircular wire, which is a one-dimensional element. And I can use this diagram, right, to find the centroids in the x and y coordinates. We know that x coordinate will be 60, but let's just find it anywhere using math. Now, if we are using Cartesian coordinates, we're going to end up with a pretty nasty integral that has square root of something of 60 squared minus x squared. That's a little bit too much to solve, to integrate right now. So let's try to do a coordinate transformation, right? Let's try to express this in polar coordinates. Okay, so let's do this in polar coordinates. And remember, if you may need a recap of polar coordinates, these polar coordinates have one component that is the radius, so the length of your line, and one component that is the axis, the angle or the rotation of that line. So in polar coordinates, instead of expressing a point here in terms of x and y, you can express it in terms of its radius and the rotation from any axis, okay? Now here, it's a little bit more complicated, right? I don't want you to think that it's so easy. It's actually a little bit more complicated because our center of rotation is not in the origin. So we may need to do a bit of extra work to find the relationship between x and my polar coordinates. But just as a recap, polar coordinates have a radius term and a rotation or theta term, okay? In this case, how do you think we can relate my x coordinates and my y coordinate to my polar coordinates? Any ideas? If I know that this point is located at radius something, theta something, what do you think is the x coordinate for that point?
R cosine theta.
Very close, r cosine theta. Well, r cosine theta will give us this distance, right? So x coordinate will be from the origin. So what will be the coordinate from the origin? Remember that the radius of the circle is, the semicircle is 60. So we're very close, r cosine theta, but we're missing this extra stretch, right? How much is that? What? 60. Remember, the radius of this semicircle is 60, which means that from the center of the circle to here we have 60. From the center to here we have 60. So if we want the x coordinate, we'll have 60 plus r cosine theta. And think of it this way, right? If we want to find a random arbitrary point r theta, the x coordinate of that point will be from here all the way to here. We know that this is r cosine theta, but then we also have to add this, which is 60. Okay? So this is 60. What about the y coordinate? Would the y coordinate also be 60 plus r sine theta?
Would it be 60 minus R cosine theta?
Let's try to figure out if that 60 is actually necessary there. Here, we see that the center of the circle is not at x equals 0, right? The center is at x equals 60. However, what about y? Where's the center of the circle with respect to y?
Minus 30.
I would actually say that the center of the circle is at y equals 0, right? Because this is my y-axis. This is my y-axis, right? So at y equals 0, this is y equals 0, we have the center of the circle. Remember, when I say that I have a line called y equals 0 is a line where every point in that line has a coordinate of y equals 0. So what I can say here is, if I'm looking at the y coordinate only, this circle actually starts, right, at y equals 0. So I don't really have to do that much here. I can say that y equals r sine theta, but I am missing something. Remember that angles are typically taken to be positive counterclockwise, right? But in this case, if we're measuring theta in this direction, what am I missing here?
Minus 30.
Exactly, right? R sine of minus theta. Just as a general, you know that sine minus theta equals negative sine theta. So just for simplicity, I'll just write it as negative r sine theta. It's the same thing. R sine minus theta or negative r sine theta, they're both the same thing. So that is all I need to do. I mean, it seems like a lot, but that's what I need to do my polar transformation, to convert this segment from from Cartesian coordinates into polar coordinates. And once we have everything we need, we can go ahead and start calculating the location of that centroid. You may remember the little steps that we had, right? We had, and I'm going to write here, our step number 1 for finding the location of a centroid was to set a differential element. In 3 dimensions, the element had a volume dV. In 2 dimensions, it had an area dA. This is a one-dimensional wire. So what do you think the element will have?
DL.
A length dl, right? So a differential element dl. Okay? And the differential element dl can be located at any arbitrary point r theta. Now, I already drew an arbitrary point r theta here, so I'm going to say that my element is here. This is my differential element dl. It's really, really, really small, has a length of dl, located at r theta. We may recall that step number 2 was to find the centroid of that element, which we called x squiggly, y squiggly. And in this case, because this element is a line, and it's a line with a very, very, very small length, we can treat it as if it were a point. So what that means is, if my element is located at r theta, that means that the center of the element will also be located at r theta. So that means that my x squiggly and y squiggly coordinates will have the same values as this transformation. We don't have to add anything, subtract anything, divide anything by 2, because this element is like a point, and where the element is located, that's where the centroid of the element also is located, because it's so small. So I can say that x squiggly simply equals x, and in this case we know that x equals 60 plus r cosine theta. Y squiggly equals y, but we know that y equals negative r sine theta. You may recall that the third step was to express our differential dimension in terms of our differential, I guess our differential coordinate. In this case, dl can be expressed in terms, right, of d theta. And why d theta? Because when we're using polar coordinates, notice that for all the points in this semicircle, right? If we're looking at polar coordinates for all the points in this semicircle, can I say that my r is constant? Yeah, which means that we can't have a dr because r is actually going to be a finite value. It'll always be there. But we can have a d theta, right? In order to have a tiny, tiny, tiny element in polar coordinates, it needs to have a tiny, tiny, tiny dimension, d theta. It cannot be dr because all of these elements have a very discernible finite r, finite radius of 60. So we want to express our length dl in terms of d theta. So what is dl in terms of d theta? Let me blow this up. Let's say that we have, this is my dl element. This is my dl, and this is just exaggerating the dimensions, right? This is my dl element. So how can we express this dl in terms of d theta? R d theta, that's correct. Good. And finally, the last step you may recall was to integrate. Exclamation mark. And integrating was pretty easy, right? Remember the equations, x bar is equal to the integral of x squiggly dl over the integral of dl. I almost wrote dA there. From step number 2, we found that x squiggly equals 60 plus r cosine theta. And from step number 3, we found that dl equals r d theta. We need limits of integration here. We're integrating theta, okay? And we're integrating theta from where to where?
0 to negative pi.
Yep. In this case, we could actually say 0 to pi because we're already accounting for the negative sign here. Okay? Because we're already doing that, we don't need to write negative pi. But it doesn't really matter because you'll see that the cosine of negative pi and the cosine of pi are the same. The sine of negative pi and the sine of pi are the same. So regardless of what you choose, it's actually not going to change your final answer. But just so that you know, we don't have to. So in this case, we can integrate from 0 to pi. And then the denominator, we have integral dl, which we found from step number 3 to be r d theta. So integral from 0 to pi of r d theta. Now, Andy already told us that r is actually constant throughout the entire line, right? It's a constant value of 60, which is given, which means that we can treat r as a constant. If we can treat it as a constant, we can take it out of the integral. So let's see what this gives us. We have the integral from 0 to pi of 60 times r d theta. We can move 60r out of the integral, right? And this will give me the integral of d theta, which is just theta. So this is 60 times r times theta evaluated from 0 to pi. We have r squared cosine theta d theta. Move the r squared out of the integral. And this gives me r squared. The integral of cosine theta is sine theta. So r squared sine theta evaluated from 0 to pi. In the denominator, we have the integral of r d theta. Move the r out of the integral because it's a constant. Integral d theta is just theta. So I get r theta evaluated from 0 to pi. And finally, we have an expected answer, right? What did we expect x bar to be for this semicircle? 60, right? So that's what we're expecting. Let's see if that's correct. 60r, r is equal to 60. So this is actually just 60 squared multiplied by theta evaluated from 0 to pi. So that's multiplied by pi minus 0. So that's just pi. Okay? Plus r squared. R is 60. So this is 60 squared. Multiplied by sine theta evaluated from 0 to pi. So that's sine pi minus sine 0. What's sine of pi?
0.
What's sine of 0?
0.
Okay, so this is all multiplied by 0. And then divided by r, which is 60, times pi evaluated from 0 to pi. So that's pi, times theta evaluated from 0 to pi. So that's pi minus 0. So that's 60 pi. That leaves us with 60 squared times pi over 60 pi. How much is that? 60. Good. And we got our expected value. Now let's see what this looks like for my y coordinates. So y bar equals integral of y squiggly dl over integral of dl. I know from step number 2 that y squiggly is negative r sine theta, so integral of negative r sine theta. And I know from step number 3 that dl is r d theta, so r times r is r squared d theta. The limits of integration are the same, 0 to pi. In the denominator, we have the integral of r d theta from 0 to pi, but we already know that that will be 60 pi. Let's save some steps here. R squared is a constant, move it out. What's the integral of negative sine theta? Cosine theta, right? So we get r squared. We know r is 60, so 60 squared cosine theta evaluated from 0 to pi divided by 60 pi. Okay? What does this give me? What's cosine of pi? Negative 1. What's cosine of 0? 1. So 60 squared times negative 1 minus 1, that's negative 2, right? So negative 2, 60 squared divided by 60 pi. Notice that one of the 60s cancels out. So we get negative 2 times 60. That's negative 120 divided by pi. How much is negative 120 divided by pi? Negative 38.2. Is that what the book gives us, Thomas? Yep. Okay, so that's good. So we found the y coordinate of the centroid of this semicircle. Now you may be thinking we're done, but remember that's actually one of the 3 segments. Thankfully the other 2 will be a little bit simpler, okay? So we want to find the coordinates of each segment here. And we found that for our first segment, the x coordinate was 60. The y coordinate was negative 38.2. And what about the z coordinate for this first element? 0. Good. For the second segment, where's the centroid of this bar? It's just a wire. We treat it as a one-dimensional line. So where's the x coordinate of the centroid of that segment?
0.
Okay. Where's the y coordinate? 20. Where's the z coordinate?
0.
Good. And then for my third element, where's the x coordinate of the centroid?
0.
Where's the y coordinate? And where's the z coordinate? Okay. You may recall that the third step was to find the area of each segment. I can just write it down here. Oh, in this case, it will actually be the length because we're doing one dimension. So it's actually a length. So the third step was to find the length of each segment. What's the length of this semicircular segment?
2 pi r. 1/2 pi r. 188.5.
Good. Or just 60 pi, right? Okay, good. I'll write 60 pi just so that we can reduce rounding error. But yeah, remember the circumference of a circle is 2 pi r. The circumference of a semicircle has to be pi r, pi times 60. What's the length of this second segment?
40.
Third segment?
40.
Good. And as you know, the fourth and final step is to solve. Exclamation mark. So how do we solve it? Well, we already know. The x coordinate of the centroid will be equal to the sum of each of x coordinates times its length divided by the sum of their lengths. So in this case, we have 60 times 60 pi. So I'll just say 60 squared pi plus 0 divided by the total length, which is 60 times pi plus 1. Right? 60 pi plus 60 is 60 times pi plus 1. Yes. This gives me an x coordinate of 60 pi divided by pi plus 1. How much is that? Thank you. Thomas, is that correct?
Which one?
X bar.
45.5, yes.
Okay. 45.5. Good. The y coordinate of the centroid is located at the sum of each coordinate times its length. In this case, we have negative 38.2 times 60 pi. Actually, I'll just write it down in fraction form. So negative 120 over pi times 60 pi. That way we can cancel out the pi's and reduce rounding error. Plus 20 times 40, that's 800. Plus 40 times 20, that's 800. Divided by the total length of 60 times pi plus 1. How much does this give us? Let's see, pi's cancel out. 120 times 60, that's negative, plus 1600, divided by 60 times pi plus 1. Negative 22.5. Is that correct, Thomas?
Yes.
Okay. And finally, our z-coordinate of the centroid is the sum of each centroid, so 0, 0, 10. So negative 10 plus 20, that's negative 200, divided by the length of 60 pi plus 1. Negative 0.8. Is that correct, Thomas?
What was it?
Z bar, negative 0.8.
Yes.
All right. Let's keep 3 sig figs. Is there anything else? 0.8 something?
80. I guess you can run that 5. Or excuse me, 0.81.
Oh, 81?
Yep.
Okay. Good. And just in time, we have solved this problem. Any questions?